I'm going through these notes very quickly. This is a lot of material, so feel free to pause anytime you need to. Please jot down any questions you have, and we'll talk about them in class. First of all, what is the degree of f of x? Well, hopefully you realize this is a degree 3, a cubic polynomial. The y-intercept, it's kind of hard to see, but these are in increments of 5. It's 0, 40. And we can see that there are 3 y-intercepts, all of which would be considered zeros of the function. One's at negative 5, 0, one's at 2, 0, and one's at 4, 0. So factors then would be the x minus the 0. So x minus a negative 5 would be x plus 5, because if I put 5 into the negative 5 into the function, it would make y equal to 0. This is x minus 2, because if I put 2 into the function, it would make y equal to 0. And same thing with 4. Now, to find what this polynomial would be then, I would merely multiply this out. So let me pause the video so it's a little shorter, and I'll just multiply this out. You guys can do this yourself and check. First of all, I multiplied x plus 5 times x minus 2, and I got x squared plus 5x minus 2x minus 10, which then that turned out to be x squared. Oh, I left a step out. Darn it. Sorry. I don't know that this saved us any time. This is x squared plus 3x minus 10 times x minus 4. Then this gives me x cubed plus 3x squared minus 10x. When I multiply everything by x, multiply everything there by x, then negative 4x squared minus 12x plus 40 when I multiply everything by the 4. And when I add these together, x cubed minus x squared minus 22x plus 40. Notice that there's my 40, my y-intercept. Also, if I put 0 in for x here, I would end up with 5 times negative 2 times negative 4, which gives me 40. So f of 0 is how you find the y-intercept. Whether it's in factored form or non-factored form, if you put 0 in for x, you will find the y-intercept. I'm going to say that again. Substitute 0 for x to find the y-intercept, always. That's how you do it. So 5 times negative 2 times negative 4 is 40. So that tells me my y-intercept. Okay, next problem. Here I give you a graph and an equation and ask you to find the zeros. Once again, you can see that this has to be at least a cubic equation because it's an odd number and it has a bend in it. So this has to be at least a cubic. If it's a 5th degree, we're not going to, and well, actually, you know it's a cubic because it's written up here, silly me. Okay, 1, 0 we can see is negative 4. And if you plug negative 4 into the function, you would see that it is 0, so you know that's correct. There must be 2 other zeros because it's x cubed. X cubed has 3 zeros. That is always true. Some of them might be repeated, some might be imaginary, some might be irrational, but it's always going to have 3 zeros. Since only one of them is an x-intercept, we know the other 2 have to be imaginary zeros. And imaginary zeros always occur in the form a plus or minus bi. Since there are no imaginary coefficients in the polynomials, nor will I give you one with imaginary coefficients, the imaginary zeros must occur in conjugate pairs. Real number plus the imaginary part, real number minus the imaginary part. They multiply together and get rid of the imaginary numbers. So let's use division then to find other zeros. So I'm going to use synthetic division here. I put my 0 in the box. So this is the 0 right here. And then I put the coefficients of the thing I'm dividing by, or that I'm dividing. Drop the first leading coefficient down below the line, multiply and add. So negative 4 times 1 is negative 4, add. Negative 4 times 3 is negative 12, add. Negative 4 times 5 is negative 20, add. And you hope, if it is a 0, the remainder here must equal 0. If the number negative 4 is not a 0 of this polynomial, then I would not get a 0 remainder. So if you know it has to be a 0, then check your multiplication or your addition, because that has to be a 0. this means this is the remainder, so this would be my constant term, my x squared term. So this is x squared plus 3x plus 5. So this means the polynomial factors to x plus 4, that gives us our 0 of -4, and x squared plus 3x plus 5. So I've actually factored the polynomial into a linear factor and a quadratic factor. And this is called an irreducible quadratic factor because it can't be factored anymore. But I can still find what the other two zeros are by setting this equal to 0 and using the quadratic formula. So I want to solve x squared plus 3x plus 5 equal to 0 using the quadratic formula. So x equals -b plus or minus the square root b squared minus 4ac all over 2a. Just help you remember the little formula there. So -3 plus or minus the square root of 9 minus 20 all over 2, which is -3 plus or minus the square root of -11 over 2. Obviously an imaginary number, so I can simplify that radical and make it an imaginary number by saying -3 plus or minus the square root of 11i, make sure the I is outside the radical, over 2, or -3 halves plus or minus the square root of 11 over 2i. So my zeros are -4, -3 halves plus the square root of 11 over 2i, and -3 halves minus the square root of 11 over 2i. Notice that both the terms in the quadratic formula are the -b part and the radical part are both divided by the denominator, and you split them up into the real and imaginary part like that. Okay, this one, how many real zeros? Well, it has 3 real zeros because it has 3 x-intercepts. That doesn't mean that we're going to be able to find them all easily, though. It means none of them are imaginary numbers, but they could be irrational numbers. So what we want to look at is what's called the rational root theorem, which says that if we were to factor this, that there are only certain numbers that could be rational numbers that are zeros. And just to remind you, rational numbers are numbers that can be written in a fraction form, or a terminating or repeating decimal, but they can be written in fraction form, an integer over another integer. They could be positive or negative. If I were to factor this out, it would look something like this. If I were to factor it into linear factors, there'd be an x, an x, and an x. The 3, the leading coefficient, would go out front. Now, since this number the constant has to be 2, it means whatever these numbers are, I'm just going to put an A, a B, and a C in here. And they might be a positive or negative, but 3 times A times B times C have to equal 2. Okay? So A times B times C have to equal 2/3. These 3 numbers together, when you multiply them together, have to equal 2/3. So there's only certain numbers that those could be. And it turns out what you do is you take all the factors of the constant, so factors of the constant, and you divide them by all the possible factors of the leading coefficient, which I'll just abbreviate LC, and that gives you all the possible rational numbers that could be zeros, so you're limited in your choices. So possible factors of 3 are positive and -1 and positive and -3. Possible factors of the leading coefficient, sorry, I just did that backwards. Positive and -1 and positive and -2, and this is positive and -1 and positive and -3, because these numbers could be either positive or negative. Now, all the possible fractions that I can make out of this combination of numbers, 1/1, 2/1, 1/3, and 2/3, all of them positive or negative. So positive or negative 1, 2, 1/3, or 2/3 are all the possible numbers that could go in these spots as a rational number. Now, either all 3 of them are rational, or only one's rational and the other 2 are irrational, because irrational numbers will always occur in pairs if there aren't any irrational numbers in the polynomial, in the coefficients of the polynomial. So if I look at these, I want to see what possible numbers do I see here that might be one of these numbers. Well, clearly this is not any of these numbers. So this has to be irrational because it's not rational. It's not in the list of possible rational numbers. This looks like it could be 1/3. This sort of looks like -1/2, but -1/2 isn't in my list. And this looks like my most promising. That looks like it's probably the 1/3. That means the other two have to be irrational. So it looks like we've only got one rational zero. We're going to divide using synthetic division. And I know this is a fraction, but trust me, it'll turn out nicely. Because my leading coefficient is 3, I'll get rid of this fraction right off the bat. Drop the 3 down. 1/3 times 3 is 1, and then this is -12. 1/3 times -12 is -4. This is -6. 1/3 times -6 is -2, and this is 0, and so 1/3 is indeed one of my zeros. Now I know the other two are irrational, and they occur in conjugate pairs, because I just explained why we can't have two more rational numbers, because one of them is clearly not in my list. That means they're going to be something like a plus or minus the square root of b. So that's kind of that's the form they're going to occur in. So to find the other zeros, I need to look at what I have left over here. So I have f of x is equal to x minus 1/3. There's one of my zeros. And then 3x squared minus 12x minus 6. That's where my other two zeros are going to come from. Now I notice that there's a factor of 3 that's in common to all these, so I'm going to actually rewrite this to make it a little bit simpler to solve. I'm going to factor out the 3, and then I'm going to rearrange so the 3 is in the front. So now it looks like this. And I told you before that if I were to factor this into two other linear factors, the -1/3 times the other two zeros would have to multiply to give me 2/3, because then times 3 would give me the 2 for my my y-intercept. So 3 times -1/3 is 1, times -2 is let's see, 3 times -1/3 is -1, times -2 is +2. So that's where we get that from. But these two, there should be two, we're going to get to two things that multiply together to give me that -2. Once again, I need to use the quadratic formula because this does not factor. So x equals -b plus or minus the square root of b squared, and I'm just going to square the -4 and make that 16, minus 4ac, 4 times 1 times -2, all over 2a. So this is going to be 4 plus or minus the square root of 16 plus, let's see, did I do that? 4 times 8, 16 plus 8, all over 2. So this is 4 plus or minus the square root of 24, all over 2. Well, 24 is 4 times 6, so this is going to be 4 plus or minus the square root of 4 would be 2, and then 6 would be left over in the radical, so 2 the square root of 6 all over 2, which is 4 over 2 plus or minus 2 the square root of 6 over 2. So this reduces to 2 plus or minus the square root of 6. So if I multiply 2 plus the square root of 6 times 2 minus the square root of 6, let's see what happens. 2 plus the square root of 6 and 2 minus the square root of 6. That would be 4 minus 6, which would be -2. And see, that gives us that -2 that we got there. So we can actually, so our zeros are positive 1/3, 2 plus the square root of 6, and 2 minus the square root of 6. If we were, the square root of 6 is somewhere between 2 and 3, okay, 2 point something. And we notice that would give me this number here. 2 plus 2 point something would give me 4 point something. 2 minus 2 point something would give me negative point something, okay, which is that number right there. Those would be those numbers here and here. So this would be actually 2 plus the square root of 6, and 2 minus the square root of 6 would be those two numbers, and there would be the 1/3. We can actually write this in factored form, which is kind of an odd looking thing, but we can write this as linear factors. Right now we have a linear factor and an irreducible quadratic factor, but let's say we wanted to show all three linear factors. It would look like this: x minus 1/3, x minus the quantity 2 plus the square root of 6, and x minus the quantity 2 minus the square root of 6. Actually, I should write them next to each other. It looks a little better. And if we were to multiply this out, we would get the original polynomial. Okay, one more. This one is different. It says we have a 0 at 3, but since it just touches here, it's a double 0. 3, 0 is a double 0, which means it happens twice. So if we want to find the other two zeros of my 4th degree, I'm going to have to divide by it twice. So I'm going to put 3 in here: 1, negative 6, 16, negative 42, and 63. Bring down the 1. 3, this would be negative 3, negative 9, 7, 21, negative 21, negative 63, 0. But I'm not done. Divide by 3 again, because I've just got it down to an x cubed plus minus 3x squared plus 7x minus 21. So do it again. Bring down the 1, 3, 0, 0, 7, 21, 0. So I have x squared plus 7. So this factors to f of x is equal to x minus 3 times x minus 3 times x squared plus 7, or x minus 3 squared times x squared plus 7. Finding the other two zeros just means setting x squared plus 7 equal to 0 and solving that. So you have x equals plus or minus the square root of negative 7, or plus or minus the square root of 7i. So my zeros are positive 3, positive 3, the square root of 7i. Let me see if I can write that a little more neatly. Square root of 7i, negative square root of 7i. If I were to write that into fully factored form, it would look like f of x is equal to x minus 3 squared, x minus the square root of 7i, and x plus the square root of 7i. So that's what this would factor to. Okay, so hopefully that helps you with finding zeros. I know this was really quick, and hopefully it was helpful.